do this better. Okay, my screen is visible. Okay, it's full screen, and I think everybody hears me. No more echo. So yes, welcome back. We'll have two talks this afternoon at the day one of the OpenGeoHub Summer School. Our first talk will be about modern challenges of geospatial data science from OpenGeoHub perspective, and we'll talk also about the project, OpenNet Monitor a bit. And I will talk about 45 minutes, then I will switch to my colleague, Leandro Parente, who is going to talk more in depth about the challenges we have, mainly computational challenges and technical challenges we have at OpenGeoHub. So OpenNet Monitor, it's a project we just kickstarted. It's a 30 million euro project under the Horizon Call governance with 20 partners, and we are happy to lead it. It will go until 2026, and we're just making implementation plan. But we have a quite ambitious agenda, and you can read, of course, about the project. The homepage is earthmonitor.org, so you can read all about the project and what we plan to make, what our main objectives, etc. We do build up a lot on the existing systems, and mainly, of course, open source and open data driven systems, including some commercial big EO data systems like Eurodata Cube and Sentinel Hub. But so we're building on top of several existing solutions, and we're trying to make up something which could result in a higher quality and higher usability environmental data. So something that we spent exploring last decade, we would like to now implement and put in action so we can generate data at faster and faster pace. We had a meeting on 19th of July. We had a public seminar day, and we had quite some keynotes. And through these keynotes, also we made a lot of notes. We invited, I think, 14 keynotes. And we made like real experienced researchers or project leaders, and they work in large European or national or international organizations, including UN, European Space Agency, European Commission. And so we asked them about data usability problems and how could we help, which infrastructure can we help to make the data more accessible, more usable. So some of the things that popped up, for example, Joanna Rauter from the Dutch Space Office, Netherlands Space Office, she mentioned, for example, that Dutch government, they spent quite some resources and funding they give for different projects, and they would like to, for example, be able to track this project in future. So they would, if there's a project about, I don't know, monitoring erosion or something, or some investment into regreening some areas, they would like to be able to see that how is this funding spent, that you can see on satellite images. And so that's something that popped up from her talk. I remember where she said, that's kind of one of the key problems we have. Then we had a very interesting talk by Gilberto Camara. So he was comparing doing local modeling versus going global. And he showed these differences, not only in the accuracy of mapping, but also in the concepts, in the legends used, how you collect training data, and there's all these complexities. So there were super interesting talks, and we're just writing now a Medium article where we're going to put all the videos, all the video recordings of all presenters, and we will focus on the 10 key challenges that we discovered during the meeting and 10 key messages, let's say. But I'm going to talk now from our perspective, what we think are the main challenges facing modern geospatial data science. That's basically the idea of this talk. And then later on in the summer school, we're going to zoom in into different of these challenges. And one of these challenges, a few of these challenges, they come up in hackathon. So you're most welcome all to follow the hackathon. So they will come up in the hackathon. And so you could address some of these challenges by joining that hackathon. And they're quite generic, as I said. There's also a Q&A in Nature Communications coming out where many of the things I'll discuss, you can also read in that article. This is like a general flow. This is basically my work last maybe 20 years. So it's a really general flow, how you can do ecosystem, vegetation, soil mapping. And it has this main phases. So starting from defining the area of interest, and then making some plan for predictive mapping, then preparing the data, then maybe spending more time to prepare covariates that will match better the processes that you want to describe. Then you can make, based on that, you can make a sampling plan. So if we have covariates, you can do some feature space optimization and to create a sampling plan. So let's say if you do Latin hypercube sampling, and then you go collect the data on the ground. Then you can do overlay, fit the models, optimize the models, and then you get the predictions. Then you can look whether the predictions are accurate enough or not. You can go back and produce the, you can repeat the whole process. So these are kind of some steps that I usually run. I mean, that's how most of our projects look like. And in the Open Earth Monitor also, we mimic kind of this setup, and we split basically the project. We have these four main components. So this is the engine. So there's the software libraries that you develop to do different processes, from overlay modeling to accuracy assessment, etc., visualization. Then there's a segment which is the ground truth data. And there's a segment which is the EO data. We call it EO data, but it's all actually gridded data we can prepare, whether they come from Earth observations, from satellites or not. And then you build these gridded data cubes, and today they're usually space-time. So space-time data. And then you have use cases, and use cases means once you have the 1, 2, and 3 working, you have a use case where you generate some models and you do prediction, and then you serve that prediction for some purpose. So that's also in a nutshell, predictive mapping. So the first step is the preparation of data. Then you have, once the data is ready, once you do sampling, etc., then you do overlay, and you prepare the so-called regression classification matrix. Then after you have the regression classification matrix, you can do fine-tuning, feature selection, optimization of model. Then you can do maybe ensembling, so the model stacking. And then once you optimize that, you can do accuracy assessment. You want to test, you do maybe some sensitivity analysis, accuracy assessment, cross-validation. And then you estimate how good is the model. And once you're happy with the model, then you do production or prediction. And then you produce maps. And these maps you can then serve through GeoServer. You can serve it through all the WebGIS solutions. And then you can do some post-modeling diagnostics to see again whether there are some issues, whether there's some artifacts in outputs, etc. And once you do that post-modeling diagnostic, you can do reanalysis, model improvements. You can create extra points if it's needed. Then you can do a total reanalysis. So you just go back and do the whole round one more time. And then if all this thing is working, then you can move to using the data for operational work. And that's also Open Earth Monitor. So in a nutshell, these are all the processes, and we've been building last 3 years. We've been building this dashboard, the data portal called ecodatacube.eu. And all this data you see in EcoDataCube, they follow these principles, and most of the data we produce are based on machine learning and primarily running a spatial temporal machine learning on really large data set. So we have now a couple of publications came out. This one is on using Lucas and Corine training points. It's almost, I think, 4 million points that overlay space-time. We prepared also Lanza data cube for Europe, almost 20 terabyte of data. Then we do a space-time overlay and we fit and we produce predictions for billions of pixels. And so that's an example in practice how you can implement all that. We also map forestry species. We have 16 tree species mapped at 30-meter resolution for 20 years. With uncertainty across Europe, we could move to mapping almost all of the tree species from the European Forest Atlas, which is 85 species. If we had enough point data, here we had a bit less point data net for land cover mapping, but still I'm talking about millions of training points. And so that's also another example of applying machine learning to large data sets to produce something that could be of usable, let's say, and of interest for different professions. So through doing all these projects with the large data, we really learn a lot about predictive mapping, and I feel really mature to talk about what are the modern challenges of geospatial data science. In this case, focus on predictive mapping, but I think they are common to many geospatial data science problems. And when I thought about how to generalize this, I tried to put it in 5 categories. We of course, there could be more categories. This is just an attempt to systematize something. So, but let's say 5 categories: training data issues, modeling issues, data distribution issues, like data distribution in sense of developing data services, then usability issues and governance issues. So these are the 5 groups of challenges that I think we could put as a systematic overview of what usually are the problems. So the training data issues that usually that could be, for example, harmonization problems, legal and technical issues, then high cost of producing new observations, modeling issues, different things. There can be problems with overfitting, extrapolation, artifacts in input data, lack of historical data, lack of consistent global monitoring stations, limited availability, quality of global covariate layers. So there are also different problems. Issues 2 to 5, data distribution issues using file formats which are not so usable, maybe not cloud optimized today. Then high data volumes. You have fantastic data sets. You have problems accessing them because they're just super high data volumes. Then you have fantastic data that has very incomplete or inaccurate metadata, so you have problems using it. Then usability issues. You can have a fantastic data, but it just doesn't match your application, so it's not relevant for decision. Then you can have data which is incomplete. Then also there are user communities, and let's say if you develop a data set and you didn't really do some homework and explore what are the user community needs, then you develop data for yourself, and you have these usability issues. Then the governance issues, so kind of data politics issues. So you can have data sets which are not according to international standards, so the international organizations don't want to use them, or national organizations. Then many organizations want this baseline estimate. So if you don't have a baseline estimate, it's difficult to make something then usable for application. Then also sometimes you make a data set, but there's no strategy. What do you do with the data set after? Who's going to maintain it? Who's going to fix problems? Who's going to convert to some next generation standard? So these are all the governance issues. We also, within OpenGeoHub, we also have, I try to list only the key issues that we have like on a daily basis. And if I had to really put it into something that really bugs me, then it was these 3. So the data size. So we suffer now with bigger and bigger data, and we have really technical challenges with the data volumes. Then we are also really frustrated with spending too much time on just cleaning other people's data. And then we have a difficulty increasing usability of data without making significant additional investments. So these are the three things I think that Leandro and me and my colleagues that we face basically on a daily basis. Every time they ask us something, that's kind of the things we have to be very careful. How do you solve most of the challenges? Well, I usually say to, especially to you summer school participants, you can solve a lot just by becoming a better coder. So you have to increase your coding skills. You have to also, of course, you have to have a fundamental knowledge of understand the problem, etc. But becoming a better coder, I think it's a certainly first thing you should consider. And then sometimes when you even do the coding highest level, you eventually reach technical limits of analysis, and in that case you also have to look at ways to get more computing power, because sometimes, you know, to increase the accuracy, once you have the best data, once you have the best code, the key is really just to have more computational power and to have more facilities to help increase accuracy. Beyond these technical problems, there are methodological problems that I would like to talk about, and this is usually the overfitting problem in machine learning, extrapolation problem, and then training machine learning models using non-probability samples. So these are kind of the methodological problems. They're not easy to solve, and that's why we also put them in the hackathon. We're interested to see what comes out. So when you start, for example, doing some modeling, and there's a lot of interest now in providing both the predictions and uncertainty of predictions in sense of prediction intervals or confidence intervals or prediction errors. And then it becomes difficult. First thing which is difficult, I noticed that if you want to do proper probability distribution, you need to know also the probability distributions into data, and often you don't know it. So that's a really challenge. There's no easy way to solve it. You get some layer and you have no idea what's the uncertainty of that layer. Then you have overfitting problems. I faced it a couple of times in my career, heavily overfitted data, because usually it was there was spatial clustering, and it's very, very challenging. And sometimes you don't see it, you just overfit the data, everything looks fine. And then later on, when you do proper cross-validation, you see that your model is basically fake. It's overfitting. Then extrapolation. Extrapolation in feature space, I'm talking extrapolation in feature space, also a big problem. I will show you some examples. Many machine learning models, they don't handle that so well. Well, we say that they don't handle it. There's a famous, I think, blog says extrapolation is stuff for the trees. And here the trees in the context are the random forest. So there are some issues there, and it's not the easy things to solve, but it's important to be aware of it. And there are some remedies, and we will be developing more and more. I think that's the task of the spatial data science, to develop remedies and solutions for extrapolation problems. Then we have a spatial clustering problems. Then even when you do uncertainty, let's say if you do uncertainty properly and you get that really realistic estimate of uncertainty for every pixel, how do you communicate that? How do you visualize uncertainty? So there's also another challenge in the modern geospatial data science. Overfitting. So as I said, I had many times I did overfitting. First few times I wasn't aware. I just thought my models are great. I had R-squared 0.9 or higher, and so I thought this is great. That's why, you know, I started liking random forest and things. But later on, I noticed that this high R-squared was not due to actual model performance, but it was due to problems with the spatial clustering. So we had these repeated observations at the same location going through the depth. And that also comes with the hackathon dataset, the USGS dataset. You have the 3 or 4 observations on multiple depths. So if you see my tutorial, when I fit the model, ignoring that there's a repetition in space, then I get the R-squared of 0.7. But when I take the whole stations out, so whole points out, then the realistic R-squared is 0.5. So you see there was overfitting of from 0.5 to 0.7. As a one remedy for the overfitting is to really try out different so-called resampling methods. So you take the training data and you resample it different using different principles. Of course, the principle that match the properties of data, and then you repeat it several times, and you just do the check. So just to be sure that you're not overfitting. So I looked at there was some discussion on Twitter. One colleague posted a data set. It's a colleague is also one of the lecturers in OpenGeoHub Summer School, Dylan Baudet. And so he posted this little data set. It's a simulated data set. Twitter is a great place, right, if you're bored at home. And then so I looked at it and I said, okay, and I think, Hannah, you made the code. You made the code for this. So I used the data set. And yes, if you so what you see here, this is the original simulate. So this is just a linear regression, and you simulate noise. So you have a x and y, two variables. Y is the target, x is the covariate, and you simulate the values just as a pure noise, a normalized noise, and then you add it to the regression line. And so you know that this is really linear regression with just a noise around the regression line. And if you do a random forest, you just use a default. You can see the code. And by the way, in this blog, you can see the code. Everything I do is there. So you can fit the random forest. And then there's a package called Forest Error, I think, Forest Error package, yes. And they just publish a nice paper that they can rebuild this probability distribution errors, prediction errors, for the random forest model. It can be relatively easily implemented. So this is really nice in our package that you can do this forest errors. And this forest error, you see here, this broken line. And so what happens first in this thing, you see that there's overfitting. So this blue line is artificially going up and down. It's trying to come close to the points. But this thing we know, because we know this is just simulated noise. So we are really fitting through noise, this curve. And so that's classical example of overfitting. And then as you go to the edges of the feature space, in random forest, because it's a tree-based learner, it basically assumes no structure in data. So it just, it will learn based on the data. It tries to come close to data. When it comes to the edge of the feature space, it uses the last decision on the edge, and then it just applies that decision because there's no more data. So it just keeps the last decision. And so that's why you see this flat line here, right? And in this case, this cutting edge forest error package also produces this uncertainty, which is almost more narrow than uncertainty here. So it looks like the extrapolation is less uncertain than interpolation. And we know that that's not true because let's say if we know that the red line is the real structure in the data, then we know that this blue line is actually going really off. Yeah, so we know that the uncertainty should be actually much higher. So that's example of overfitting and also example of extrapolation at the same time. Now, what I did, I said, okay, well, let me look at my framework that I use for work, and I like to use this ensemble learners by stacking. And I put, I think, 4 learners, and one of the learners was a simple GLM, and the other learners, they were more complex, random forest, XGBoost, I don't know, some other methods. And I put it, and then this is the thing I got after ensemble machine learning. So it does work a bit as a remedy for the overfitting. So you see it's much less fitting if you compare the 2 lines. So there's a much less overfitting. And as you go towards the edges of feature space, you can see the uncertainty. It's kind of what we will expect that it grows. It's actually a very similar plot when you have the prediction errors in linear regression, right? You have this curvature of the confidence interval as you move from the center of the feature space. And so that's just an example. There are some remedies if you want to deal with the extrapolation problems, let's say. In this case, the remedy was to use a combination of simple, like linear learners and non-linear learners together. And if you use that combination, and you do the ensemble by stacking. The stacking eventually picks up as the best algorithm is the GLM. So it's not the random forest, actually random forest you could take out from this system, but it finds it automatically. So I didn't have to, specify anything. It's just, it finds it because it does repeated like 5-fold or something, cross-validation, and it finds out. So there's this criticism on extrapolation, and Hannah, I think she already in summer school in 2020, Hannah gave this talk about area of applicability and all these problems of going outside of the training feature space. And there's this piece, there's this article they publish, Hannah and Edzer, in Nature Communications, where it's a bit critique piece, where they ask whether extrapolation should be implemented at all. Maybe you should just mask out the pixels. And so something we can discuss. Also, when you think about this, we also have lots of machine learning papers where we predict the future. So we predict distribution of something in future, given the climate scenarios, given some changes in population, I don't know. So we also do prediction in future. So the question is, should we also extrapolate going not only feature space, but extrapolate in time? And then how do we communicate? If, let's say, if we do extrapolate, how do we communicate effectively uncertainty and overshooting? How do we communicate this? Here I do this, confidence prediction intervals, but how to do that with maps, how to do that efficiently. So you can read that paper. I don't know if you saw it, but in Nature Communications, and they speak about lots of these problems. Here's a paper we found. This group, Jülich Research Center, they actually develop a framework where machine learning is combined with uncertainty assessment, and they do also produce these maps of applicability. Everything which is darker, all these darker colors means it's feature space, which is there's no training points. So you see that's a serious problem. I mean, many global data sets are like this. You don't have a probability sample, but you have this usually large gaps, especially northern hemisphere, tropics. You have these large gaps that are really not easy to access. There's not many points. And you can see that, and apparently this paper, I haven't studied in detail, but they do a really thorough job of checking uncertainty of each input layer, and then thinking how to incorporate these uncertainties to see how much do they impact the final uncertainty of predictions. There's another paper just popped up, and Cecile Brown, my colleague from the Waag University, and colleagues, so they publish on the problem with if the data are clustered. So can you really do estimation? Can you do unbiased estimation if data is highly clustered? And so they simulated these cases where you have no clustering and really high spatial clustering. So there are different combinations. And so I think the conclusion they came up to, as far as I understand, if the data is, for example, like here, highly clustered, that you cannot produce unbiased estimator. So basically, with this type of data, you shouldn't be making maps at all. So if I understood correctly what they claim, because there's no way to avoid bias. So, and that means that this data, you should just stop and just go collect the funding and collect more point data. The problem is if you do space-time modeling, and if you want to do space-time modeling, how do you go back to past to collect data? So, something it's mind-blowing, but, we cannot make a time machine, right? So then the question is like, do we really just drop the whole field? Or is it more that maybe we can do unbiased estimation, but we need a different method because this is only in the context of the method they use, right? So that's a question. Can we have a remedy for that, or do we really drop it completely? Do we stop doing that modeling analysis? And this is a really serious challenge because on one side you have, for example, policymaking, governance organizations. They need data. They says, give us an estimate how much, I don't know, forest we have in Europe 200 years ago. Give us an estimate. Give us the data. So they're data hungry. On the other hand, we have like strict statisticians saying, well, don't do estimation because you make a bias. So it's really challenging. You feel be divided between the two. I participated in this paper together with Surya Gupta. He just finished a PhD at ETH, focused on saltwater characteristics. And what he did, he got this data set. He spent, I don't know, 2 years, collecting, cleaning data, checking data, opening reports, papers, and this is the best he could create. So this is the best he could create. And there was a lot of problems here. Like the Florida had about 10 times higher density of points than the rest, so you have a high spatial clustering. Then you have these huge gaps, Latin America. Luckily, we got data for Russian Federation. But there's still lots of places no data. Of course, arid areas, deserts, we don't have any training data. People don't go to desert collect soil samples. It just doesn't make sense. Also, so there was these huge gaps, and so the question is, was this data set? We made the maps, we published this paper, but the question is, how much of the effect of the clustering? How much does it touch our estimates? Our estimates may be biased in a way. Did we, for some areas, did we produce really something where uncertainty is so high that we're making wild guesses? And as I said, the big problem is the spatial temporal models. So how do you validate that? How do you go to the past? How to do that? So it's not something easy. Maybe for some things we'll never know the truth. We'll never get even close to the truth. But on the other hand, when you look at space-time, you can do sometimes what you can do in space-time. You can build the models. For example, if you say, I would like to predict in future, so you could go back to the past and fit the models for the last 30 years with the data we have. And if you fit the models for last 30 years, and if you find significant relationships, then it gives you some confidence to extrapolate that into future. So as long as you can reconstruct the past, that gives you some confidence to predict the future. But future is also, it's non-linear, so nothing is standard, and it can get really complex. Visualization of uncertainty. When I was a PhD student, I looked at this whitening techniques. You use the hue, saturation, intensity, color model, and you use the color hues to visualize the values going from bluish low values, reddish high values, and then you mix in the whiteness, and so you kind of bleach the map, and you can see here different variables, and this variable has a high uncertainty, and this variable has a higher certainty, let's say less uncertain pixel, and you can see these are the results. On the left, you see the original predictions. On the right, you see predictions visualized with uncertainty. Now, if you show maps like this, like a kind of bleached, it's kind of like buying a painting, and then your painting, instead of having really nice colors, it's kind of bleached, And many of you probably go like, well, I don't want this. Can you give me the one, without this whiteness? Because it's a bit annoying, right? That you go like, but this is the reality. It's like a cloud, if you have a high uncertainty, if the uncertainty is higher than the variance in the data, that means that you're really just making wild guesses, and it gives you right to paint it as a white, because it means basically we don't know really with high enough certainty what's happening here. This is visualization of uncertainty with prediction intervals, also very useful technique. But how do you do that with maps? You need like a tree maps to visualize one thing, and how to do that. Especially if you have a 3D data or 3D plus time, then you have also confidence intervals. Then you have these multiple dimensions, and it's not easy to visualize. Then there's also beyond methodological problems, there's usability problems. It's a great paper by Julia Wagemann, and they did these interviews and polls, and they collected all these things, and they came up to these challenges of bigger data. So they are listed here, limited processing capacity on user side, growing data volumes, that's something we had also. I think that's common for many fields. Non-standardized data formats and dissemination workflows, too many data portals. It is also more and more problem you get like hundreds of data portals. Even for the same field, you have today, I think, 4 or 5 global land cover mapping projects, and people are starting to get confused. They're lost. I mean, which one do I use? And it just costs you time just to make a decision, which data do I use? And then difficult data discovery. This is an example, fantastic data set, paper published, scientific data. We downloaded the data set. It was just tiles, I think. And then we downloaded the tiles and we built these mosaics for the whole world. And this is the Sentinel-1 seasonal data, 4 seasons. So you can see, this is Wahina, so we are. You can see for different seasons, different bands, how things change. And but the problem is when you download the data, you create a global mosaic, then you discover there's all these gaps. So it's a fantastic data. It's based on the Sentinel-1, cutting edge technology. But it's about 91% complete. So you have about 9% pixels are missing. And we wanted to use this data set in multiple projects. And because this missing 10%, we cannot use it because if we miss this data, it will propagate to anything we want to do. And so we had to drop this data set just because it misses 10%, because we cannot deliver something which is also on our side also 90%. These people managed to get this data set out, but they didn't, let's say, fill in the gaps. I don't blame it on them. I think they didn't have the Sentinel data. But this is an example. And also then you have these artifacts, lines, etc. As I said, also big challenge of data science. Realistically, I think you agree with me also, 60% of time what we do is we clean up other people's data. You're lucky this hackathon, we spend that 60% of time to clean up and prepare this data. But in many projects, when you start, you will spend from 12 months, you will spend 6 months or longer just cleaning up, organizing, checking tabular data, layers, GIS, importing and stuff. And it's a real pity. So that's it from my side. This was a big overview from my 20 years of work experience and also from the EcoDataQ project. And just to announce our Open Earth Monitor project, now I pass it on to my colleague, Leandro, who's going to talk about the OpenGeoHub perspective on handling large geodata.
Leandro needs to sit there.
Yep.
See if you can just walk.
Okay, so thank you, Tom, for this very nice perspective. So basically, I will explain how we are kind of trying to manage these problems that Tom explained, and what solutions we are using to really develop our applications and do our mapping products. So I will start with this funnel pipeline. So basically, we have several applications that we implemented internally at OpenGeoHub that we kind of, the code that we wrote, it's basically a kind of funnel pipeline that was able to reduce the data input that we have mostly, and in this case, in this example, for Earth observation data, so climate data, satellite data. So we have several kind of raw data sets out there, and these kind of Earth observation data sets, they are not a commodity at all. You need to do a lot of work, and not only to do the modeling, but also to do the prediction and generates like complete maps. So, considering this data volume, I would like to emphasize that this kind of funnel pipeline, it's a way to reduce this universe of raw data to like a lower and more compressed data volume in a way that allows us to really develop the desired applications. Of course, you have some implications with that. There is no free meal, but basically I will show two examples of it, but basically this full pipeline, I would like to emphasize that we use kind of this cloud computing like available, so AWS, Google Cloud, Google Earth Engine, and more recently OpenGeoHub platform. Some of the archives of Sentinel Landsat, they are like petabytes of data. And so you can use cloud computing to kind of compress, reduce, and export this data from these platforms to in-house computing infrastructure. So, and this, it's what it's called like hybrid computing infrastructure. So we combined both of the best of the both worlds. So, and why you would like have your computing infrastructure. So for example, why we have our computing infrastructure, when we prepare this data set, imagine like Sentinel, Landsat, so we prepared several collections for Europe. And when you start modeling, you can use your own infrastructure to really, for example, do predictions and see the results and do all this, implement like the whole workflow in your own computing infrastructure without spend credits in the cloud computing. So, and of course, you cannot host the entire Sentinel or Landsat archive internally. We are talking about petabytes of data. Maybe with a lot of money, you could have a computer center able to do it. So currently, that's kind of the architecture that we have. And basically, I think it's a nice thing because it allows us to really play a lot with the data and see, and for example, implement different gap filling approach, not for like very small areas, but for large areas, and see what are the impacts at global and continental scales. And of course, doing it properly, you improve the quality of your output. And basically, there are some simple stuff that we do, and there is a cost on it. Of course, you need to consider it. So, for example, if you have like this, the Landsat and the Sentinel data, most of this data you can find like in integer, and there are some data that are available at floating 32. So you can just convert it to a more like compressed range. And so it will reduce a lot the data size. Of course, introducing for some applications might be sensitive. So I don't know, maybe for some forest land degradation could be in fact. So you need to test. But doing this simple like conversion and reducing it, you can really compress the range and reduce the data size. Other thing that we implement is actually this temporal aggregation. So basically, for example, you have for Landsat 16 days of temporal resolution. For Sentinel now you have 5 days. So, and maybe you don't need like a very dense time series. So maybe one monthly time series would work, a bi-monthly time series would work. So you can actually process in the cloud and aggregate different time intervals, generating, for example, one temporal composite for your application and downloading it. So that's one way that we are also implementing. And for some case, this is more like it's not really, it doesn't fit for all the applications, but for example, you can also reduce for coarse resolutions. And we did it for with MODIS. So we did, for example, some experiment to harmonize MODIS data that it's available since 2000 with AVHRR data. It's a kind of long-term time series available since 82. And this data is just like 1 kilometer. So for this case, just like a coarse resolution was perfect to try to harmonize both products. So it's more limited, but it's also an option. So here it's one example. So in this case, basically, we took all the MODI 13 key 1, the vegetation index product. And we also have this product internally in our infrastructure. All the product you can download from NASA, but you will download several tiles, HTF files, aggregated bands. So there is quite some work to download and process it. So
16 terabytes.
16 terabytes, right? And basically here, these first two steps we implemented in Google Earth Engine. And so we removed the low EVI values, considering like the pixel reliability. It's a quality mask in this product. And we did bi-monthly aggregation. So this is a 16-day product. We aggregated by every 2 months. And we exported it from Google Earth Engine. And so these two steps implemented in Google Earth Engine. So after the implementation, when we exported the data, took 1 day. So with 1 day, we selected the desired band, removed the cloudy pixels, the pixels with shadow and clouds, and implemented this temporal aggregation. After that, we had like full flexibility to implement in our internal infrastructure, like several gap filling tests and considering, for example, different land masks to reduce the pixels only to land and removing water pixels and things like that. So in this example, we used the Google Earth Engine, exported the data, and did all the rest internal in our own infrastructure. Now, as we have this data, we will do it for all the bands. We will just use our internal infrastructure. But it's one example that if you are interested in only one band, that's a nice solution. So basically what we did, so this is the output that Google Earth Engine exported to us. It's aggregated 2 months, so January 2010. So we use it here. We use it not all our servers, but all the threads here were used to implement this gap filling, and it's temporal gap filling. So basically, when we don't have like observation in January, for example, it will look in other Januaries, and it will look in like neighborhoods months in temporal, but it will focus just like in other observations for that pixels in different periods, mainly. And of course, there is a cost on it. So, and considering your application, maybe it's not suitable, but we also generate a kind of gap fill flag. So you can actually know this pixel, it's original pixel or it's a gap filled pixel. And you can decide if you use or not. We are providing so both the product gap filled, but also like a metadata information per pixel. So it allows the users to take the decision. And this is the output. So basically here, we can see like this time series and basically the how it's a kind of the earth breathing. So and
it's like a heart beating or something. It's a similarity with the real life and organism. Yeah.
Yes, and for some areas you have these seasonality aspects, and this is the size of the data set. So it's a complete, consistent, and full data queue. And in the end, we organized it in a stack. It's not really like official, this stack for the Open Land Map. We are working on it, but you have all these layers like ready to go with the flag indicating if it was gap filled or not public available. So, okay, this is modes, but so Tom asked when I entered in the OpenGeoHub, so yeah, I want to work with the Landsat data, and I want to go to 2000 and really get and map the big shifts and what is happening at 30 meters. And to work with the Landsat data, you have mainly, Landsat, it's a great data set, but you need to always remember that it's a long satellite program, the longest actually. And when you talk about it, you have different satellites, different sensors covering all the period. So since 2000, we have Landsat 5, 7, 8, and now we have 9. And USGIS, they do mostly, they do a lot of work to try to harmonizing it and to put all these observations together. But you cannot really cross-check and have a consistent time series observation, because basically the sensor is different. The sensor, for example, Landsat 5, it's old technology, and You have till 2000, 2010, mostly Landsat 5. So you need to, considering that all the sensors are producing like different data sets and different values actually for the same aspects of the landscape. And it's tricky. So when you mix all these observations and to do what Tom explained, this spatial temporal modeling, you are actually using one single model to map Landsat 5 and to process Landsat 5 and Landsat 8 and like map what is the land cover, what is the soil, what is the tree species in that specific pixel. So you need to have a highly harmonized data set. Otherwise, you will just see some trends and patterns that it's doing the data, not to what is happening in the landscape. So considering it, you have a few harmonization techniques to do it. And when I started, I found these two mostly the interesting. So we have the GLAD Landsat R&D. So this is an initiative developed by University of Maryland. They have the whole archive internally, so petabytes of data, and they processed everything and did a proper harmonization and produced a very nice product that you can really compare and cross all the values through the Landsat 5, 7, and 8. And they are using it for all their products. So it's really nice. They have several products, and it's a very tested data set. This is one thing, but they release the data, but they don't release the software. So it's the software, it's private property from them, but the data is free. So you can download, you can access an API. But if you want to download, for example, I don't know, the whole Europe or an entire continent, the speed is not great. Even in US, we did some tests. So for example, just to have idea, to download all this data for Europe, it took 1 month just to download and put in our since 2000 to 2020. So it's a large data set, but it's also there is this bottleneck in the way that you can access the data. This is one solution. The other solution is the FORCE. It's a very nice solution. It's a software solution. Initially, it was developed inside of the University of Humboldt. And basically here, they also add the Sentinel-2. So they have one approach to harmonize everything, Landsat and Sentinel, and really do the reprojecting, the gridding, generate the temporal composites. But here, they don't do it you don't have like a data available from FORCE. They have just a software, so you need to process by yourself. I know now there are some initiatives that are actually working with FORCE, processing the data and put it available. But mostly the work that we did was considering this GLAD Landsat R&D because the data was there. So, and even considering this data, we still need to remove the clouds, the shadows, and implement the gap filling. So if you add a new harmonization pipeline on it, it would be a lot of processing time also. So, and here it's just like a conceptual explanation. So mostly as in USGIS, they deliver level 1, level 2 products. And now they are, I know that USGIS, it's deliver also some level 3 products. But FORCE and GLAD, they are mostly in level 3 and level 4. So temporal composites, gridded data. And so here's an example. So if you download one GLAD tile, you will have all the Landsat bands, one additional KA mask, so quality assessment with indicating where is shadow, snow, cloud, and this stuff. And basically, of course, if you remove it and the pixels where you have cloud, you need to gap fill. And they are putting everything available, and you need to do a lot of work even after the download. So they organized also this composite interval. So this is not like a one image for a specific day. This is like a temporal composite. So it's a level 3 product. So for example, the first composite covers 1st of January till 16th of January. So you have observations for different dates inside of this time window, but they are completely harmonized. And also observations from different satellites. So you can have like 1 pixel from Landsat 8, 1 pixel from Landsat 7, and things like that. So considering it after the download, we did like a cloud removal, temporal aggregation by quarterly, and matching with the seasons, gap filling, and mosaic. So even after all this harmonization process, we still did a lot of work. And here is one example. So we are working with this data for several areas in the world. So Europe, US, Brazil, Canada, and this is an example in Canada. So covering this period. So this is a temporal composite from 13th of September 2019 to 1st of December. And for all this period, these blank areas, we didn't have any observation. Maybe because the satellite couldn't obtain an image, or maybe because it was cloud or low quality. So considering it, basically, we used our gap filling approach, considering other observations in time, and we did the gap fill, right? We filled these gaps with a valid observation, but again, maybe the observation here could be like from 1 or 2 years ago, and there is impact depending of your application. So we are always providing the flag mask, the gap filling mask, indicating what pixels are true, what pixels we did gap fill. This
Okay. Do we have to do anything?
So here, just full screen.
Yeah, I can find.
You find it somewhere.
Here.
This one. Okay.
Okay, sorry. We are
Can you check your audio?
back. Let's see.
This one.
Yep, it's working, right?
We just have to switch.
Ah,
to
sweet.
That's okay. It's okay?
Yes.
Okay.
Sorry about that.
Sorry about that. We are back. And so this is what we are seeing with the Landsat, and this is what we can see with Google Maps. So it maps. And of course, if you are looking it in the middle of the Amazon forest and you have a deforestation and you had a gap there in the same place where you had the deforestation, you will not see. There is no magic. But for the most part but for a lot of applications, I would say it will fit. So, okay, and how we are doing it, like really using our computing infrastructure. So basically we have several, I would say, like large capacity servers. So instead to have, I don't know, 30, 40 mid-range servers, we really invest like in high capacity servers with most number of threads possible. So considering the budget, of course. So mostly of our servers now, they have 96 threads and half terabyte of RAM. So it's a lot of RAM and a lot of threads, but if you want to work with these servers like in an integrated way, you need to set up a HPC infrastructure solution. So basically what we did, we are using mostly Slurm to split the job and basically send for each of the servers a chunk of data to be processed. I will show it with a conceptual example. But for example, you need to send also the code. So you need to develop like some R or Python script and send it to be processed, and it will be like a prediction or a gap filling approach. So all the servers need to access a kind of distributed file system, and we are using Samba. It's not the proper one for high performance computing, but we are using to have compatibility also with Windows and access these servers through Windows. But for that, we are not using Samba to send data or to access data. We are just using Samba to send, for example, the scripts and the code to be executed. To send data, basically, we are using Min.io. It's a self-deployed solution that implements the S3 protocol. So imagine that you have all these cloud object solutions, S3, Google, and they created like a internal, like one solution that you can deploy in your own infrastructure and has all the advantages of this protocol. So it's highly reliable for like HPC. So for example, when we have like that image that I presented of emojis with several gaps, I can put it on S3 and I can have several servers accessing it. Of course, it will be a bit slow, could be a bit slow because of the network problems and bottleneck to access it through the network, but it will not crash, what is most important. So it's highly reliable and it manages really well like the high throughput to data access. And to get all these libraries and processing running, we are using Docker. So we have our own containers with GDAL and the main R libraries, MLR, MLR3, and raster.io, and we implement the development of these scripts. We do it with RStudio and Jupyter Lab, but to do the processing, we actually send the command for all the servers, and we create a new container with the same libraries, so with exactly the same environment that we did the development of the script. So it's highly reliable also. So we will not like crash any machine because you are using the wrong library. It's the same environment. So basically here we have the short explanation for all the solutions. One thing that I would like to say is in the Min.io, mostly we are hosting the cloud optimized GeoTIFFs. So we did some tests with TileDB, this ZAR format and things like that. But for me, cloud optimized GeoTIFF is the best solution right now for us because it allows us to visualize the data. So it doesn't, I don't want to have like a TileDB representation of I don't know, a very dense time series or even the emojis data that I could not see, that I cannot see, because I need to access the data. We work with geospatial data, so I need to access and see and analyze it and see at the global scale. So the cloud optimized GeoTIFF, when we did this evaluation, it was the only solution that provides the pyramid layer. So I can have the same data structure and the same data format to do processing, but also to visualize in QuantGIS. Of course, if I use TileDB, maybe it's more reliable and can access more, receive more access, but it's not easy like to visualize at global scale. Imagine it has all the pixels of Europe and try to visualize it because it doesn't have like an overview structure as cloud optimized GeoTIFF. I will talk more about it during my Python session. And yes, so all the Docker containers that we are using, they are public available in Docker Hub. So you can just start using if you want in this RGO IDE. You have the last version of GDAL, Terra, MLR, everything ready to go, and the same in Python. So everything really integrated, and you just start the container and can start working. So this is one example of processing that we do. So this is the Landsat data for Europe, and we started creating what we call like a tiling system. So in this tile system, it's basically place where we have data considering like a predefined grid cell. And here it's a 30 kilometer by 30 kilometer. So it means that 1000 by 1000 pixels. And basically we sent chunks of this data. We split the data in different CPU servers. And these CPU servers, they access the file in the storage server. So you have a kind of bottleneck in the storage. And of course, if you are doing like a minor computation, I don't know, some NDVI calculation or something like that, might be the access time might be large than or bigger than the processing time. But for the most part of the applications, that's not the case in our case. So for example, the gap filling is highly computational. So once that you load the data, you can load just that chunk and do the processing and later write it back in the storage. So this is the first step. So first we send all the servers start processing different chunks of the data using the same script. It's parallel computing. Basically, it's the same code executing in different chunks of the data. And here's an example of our expanded infrastructure. So we are using all the threads, and mostly this analysis was performed to calculate the gap filling and the trend analysis also per pixel. And after that, we just write the tile that we processed, we write it back in the S3. So in the end, you have like all the tiles, small tiles, not the big mosaic. You have small tiles in the S3 ready to be mosaiced and to do the mosaicing. So to do the mosaicing, basically we use GDAL. We build a VRT and we use GDAL Translate or GDAL Warp to transform all these tiles in a cloud optimized GeoTIFF file and write the big mosaic. And later we just drop all the files. So you could try to use some parallel writing. So I know that there are some solutions trying to do it. So you could have like a big mosaic and you can put all the servers to write in different positions of this mosaic. But again, if you have something like that, still you need to convert in the end for a cloud optimized GeoTIFF to have a full picture of your result. So that's why we are just using cloud optimized GeoTIFF internally. We starting testing TileDB, but for me, yeah, still cloud optimized GeoTIFF. It's a nice solution because it brings also the pyramid layer and the overview of all the area. And mostly of this processing, it's implemented in this Python library. We call it UMap. And you have also several tutorials here and the gap filling, the overlay. So I used this library to implement the overlay for the hackathon. We have also like a class called Land Mapper that implements that use all the scikit-learn models to predict and do the modeling, but also predict. So it's a kind of wrapper for the scikit library, scikit-learn, and in a geospatial context. So we have some wrappers also for GeoPandas and Raster.io, but it's mostly like we try to put all the routines that we implemented here and keeping using it mostly for our applications. And yeah, I think I can pass to you and you can.
Yes. Well, you can stay and then we'll have some questions and we don't have to switch.
Okay, but do you want to make the conclusion?
Well, yes, just to conclude, yeah, you saw some challenges that we have. Some challenges are methodological, some challenges are because, you know, the complexity of data or spending a lot of time cleaning other people's data. There's also many technical challenges, and Leandro shows you with the real examples the challenges we have, for example, with you know, something like a really world-known Landsat and Sentinel missions, and then once you get into them, and if you want to do like a space-time analysis and modeling, you immediately notice what we saw, that, you know, there's harmonization issues, there's gaps, there's some artifacts in the images, and it also sucks time, and you have to do this gap filling aggregation. So there's a lot of challenges, and I think the challenges that will remain is also this one, the 5 groups we mentioned: the training data issues, modeling issues, data distribution issues, usability issues, and governance issues. They will change. Maybe I missed some aspect here. If you come up with something, please let me know. And we live in amazing times. I mean, I've been in this field 25 years almost now, and it's really amazing time. There's the satellite data is now publicly available. Then there's the open source software. It's really amazing. It's amazing developments, and we also have hardware-wise, we have now possibilities to process large data sets, even with no budget, just using Google Earth Engine or OpenGeoHub Cloud. So without any budget, you can really do magical analysis. But it's still, even though it all looks really bright and great, you will see that when you start doing real projects, it takes careful planning, testing, and that's why we actually also do that hackathon. We created that hackathon out of this lecture. It's really connected. So in the hackathon, either of the hackathons you choose, you have to do very careful planning. You have to, first see what's possible if you will have enough time. And then for the second hackathon, you do this sensitivity analysis. So you can create functions that it's not about maximizing accuracy, but it's just checking how bad could your modeling go, and how how sensitive is the data and all the software you have, the algorithms, how this sensitive are they to extrapolation, to spatial clustering, etc. And with this thing, yes, I think we can close the sessions. We are now looking for questions, if there are any online questions or questions from here. I don't know how many of these things were new to you. Slurm, I mean, I don't know how many of you use Docker. How many of you use Slurm? Let's see. Oh, I see quite some hands. 1, 2, 3, 4, 5. So that's a high level. It's a high level programming. It's when you have lots of lower level functions, you combine them so you can distribute the computing. It's also a scripting, kind of a scripting interface. Yes, please, questions. Yes, Ben?
I have one. If you're working on tiles, how do you deal with the edge effects? So if you just do you have a kind of overlap or something? How do you solve that?
Yes, it's a good question. Absolutely. There are applications where, let's say, the edge effects are a marginal problem, right? But there are applications where you have this proximity and spatial dependence. So if you will tile, you lose that spatial dependence, and then you have artifacts. And I had the problem with exactly what you're asking. I had with the hydrological modeling in terrain. So when you do hydrological models, the watersheds, they go beyond the tiles. And when I started doing with tiles, of course, the first time I just tested, okay, this is ridiculous. I get the lines, so it's not going to work. So I made in my landmap package, I made a function when you do tiling, you can also specify the overlap. So you have these tiles that overlap. And so then you model with that overlap, and then you cut out only the center. And then you glue it like that, and then you don't see the lines. So that's one way to hack that problem, let's say. But yeah, it's not simple. Yeah. So one solution would be to have the overlap, tiles with overlap, and you can even have the whole tile overlap. So it becomes like a filter, like a moving filter, right? You have a tile which is like a 3x3 tiles, and then you do analysis, but you only take the results from the middle, and then you move to the other one. So that works. I tried with actually for whole of Africa like that.
Well, I guess it depends also on the spatial range, on the dependency you have in your data set. So you have short dependencies or long dependencies. And for the gap filling, you're doing it space and time-wise, right?
No, so the question is for the gap filling that Leandro showed. The algorithms they use now are purely temporal based, so they look at the temporal neighbors, so either January last year and the year after, or the February, March, but it could be combined with the spatial, so you do both spatial and temporal. But for example, spatial, you do, it's very important that it's like really edge, edge around the pixels, because as you move further in space, you could be really, extrapolating something. So I think, I believe in what Leandro does now, this temporal filtering with, especially when you have like 30 years, then you have so much neighbors in time, that I don't think you need spatial. But it could be also combined. There's also functions we made, I think, in the project where we force removing the pixels. So we have the pixels, but we remove them randomly or something. And then we do cross-validation. And then we see whether some algorithm, for example, is better than the others, if something sticks out. And we did that, right? Maybe you said that about it, please.
We did that to analyze with, because you can also just do a kind of linear model. So it will, considering the whole time series, it's not perfect. You can also have, for example, like a gap, and you just do like a linear model between the closest observations, like a straight line. So there are some ways to do it like in a temporal domain. Basically, what we are doing, we are expanding like the window for the neighborhoods and taking the average, but not only from the pixels from the past, but also from the future. So depending on the application might have some implications. So for example, for a more conservative approach, it's just in a temporal domain, it's just keep the last visible observation. So you make sure that, okay, this is the last land use and land cover, so I will not overestimate or bring some land cover change from the future to propagate it to the past. So it depends. But so the way to assess it like objective, it's just creating artificial gaps, and you test out these different models, and you can compare with the ground truth of the artificial gaps. And for the spatial, we have also some other methods, but it's a kind of like kind of weighted average. So when you are really close from, you have like huge gaps, it doesn't work really well. It's just like a kind of poor interpolation. So in some case, you don't have pixel at all. So because maybe the satellite doesn't cover that area, or it's close to the coastal and they are limiting the data there. So in some cases, we still use the spatial, but after the temporal gap filling.
Yeah, I was thinking about the deforestation use case. So all the neighbor pixels are deforested at some point, but kind of the one you miss is kind of still forested. That might kind of also indicate an error we could use kind of spatial neighborhoods to kind of improve the gap filling. But you can kind of construct any example in any direction, I guess.
Yeah. The best is to do this against like sensitivity on accuracy testing, and to like also take some kind of probability sample, take out the actual pixels, and then test different gap filling algorithms. That's, I think, the best way to go, and then apply. But it also depends on the context. What Leandro said, depends what the application is. If the application is only like deforestation, maybe there's some other gap filling will work for that. But if the objective is just to fill in all the pixels for all the land cover, and as fast as possible, because we don't want to compute 1 week, right? Then you can take something more simple, I think. Yeah. But it's also important that what Leandro says, let me emphasize that one more time, everything we gap fill, we provide a mask and we say this pixel is gap filled. So it has to stay. It's very important for science that you keep a record of any manipulation you do, and that you specify that there's some gap filling being done. So it's not like actual image, it's a gap filled value. So people don't, if there are issues, that they can back trace and says, oh yeah, I have this problem here, but I see it's because you gap filled. So something happened during that gap filling that, for example, you don't see some deforestation or something. And I also have a question for the people. Are you using TileDB as a data storage? Anyone? It's a very attractive solution, and it's a multi-array data cubes. And we tested it as a geospatial TileDB. It is compatible with GDAL, so you can convert. But you see, one little thing about this TileDB, I think it could be that it's faster for some things, right?
Yeah.
And it's very, imagine it's beautiful. Like you can put this multivariate data, space-time data. You put it in a one file, and it's a database file, TDB, I think. It's a database file, and then you put it in S3, and many thousands of people can access it and program with it in Python, in R. But you want to visualize it, and problem. You have to export from TileDB into GeoTIFF, and then you put it in QGIS, and then you can see it. And you see that little thing got us not to use it, because we tested it. Actually, Leandro put the whole MODIS, for example, time series, space-time. He put everything in one file, TileDB. It's beautiful. You just take the whole temperatures from MODIS, and you put it in one TileDB file. So you can, and you can just, this is like a database. So you can connect to it, you can extend it, you can search it, you can subset, you can do overlay, you have, sky's the limit. But to visualize it, you have to get it into GeoTIFF, and then we realized, oh, it's a pain, and we dropped it, and we just stayed with the Cloud Optane GeoTIFF. And Cloud Optane GeoTIFF, I think most of you use. If anybody is not using it or needs some introduction, just raise your hand, please. We have to know now. So so we will do a cloud. Leandro will do a gentle introduction to Cloud Optane GeoTIFF. On the end, it's nothing special, but it is magical that you have just an image file which has basically indexing inside. It has pyramids. It has like a tiling system, and so when you start doing visualization, overlay, subsetting, it goes so fast, and you can have again 1,000 people connecting to the same file and using it without downloading whole file. So that's a session that's coming on Wednesday. Yeah, so you can follow that. Yes, Jakub.
Thanks. So I have a question about patterns. So probably you know that with ecology, often we know that it's not only about the value in some place of certain thing or the land cover category, but it's also about the spatial relationship between those categories. So there are different biodiversities depending on spatial patterns and so on and so on. So from what I heard already, I guess that you are not considering that while building the model, but do you plan to do so, or do you even consider that in some future steps?
It's a good point. If I understand you correctly, so like in the first hackathon, we are just asking who will get the best predictions at test points, right? But you say, well, what about, you get the quantity, you estimate quantities, but what about the patterns and shapes? And yes, I'm not sure what is the best metrics for that. And like maybe, do you have a robust metric for how well you match the shape? I mean, imagine if you have a land cover system and you want to map the buildings, let's say, and then all the buildings are like squared usually, and also, of course, they cannot be too thin. They cannot be too long, So you could, but what is the one robust measure for that? Do you have maybe? Is there one robust measure of the pattern accuracy, or?
There are some ideas, and there is nothing which is one perfect solution. With patterns, the ground truth doesn't exist, and so that's probably also like a huge problem for machine learning.
So, but it's for sure for the land cover, also deforestation, the shapes and the spatial proximity and all these things. Absolutely, we ignore it. Many projects just ignore it. They just do like points and whether the point is correct or not.
And especially, I think that it would be very useful with your land cover for the next 2 years. Like you have the same product going for 20 years, and keeping this spatial consistency could be important. Just an idea.
Absolutely, no, I agree. But just we don't know how to do it. That's the. Okay. More questions? Is there any questions online? Participants online? No?
Oh, there is one there.
We have quite some people watching online. We are very sorry you're not with us here at the summer school. But if you have questions, please. Yes, question, please.
Yeah, I have a question.
Marcus.
So you were saying that 60% of the time goes to data cleaning, and the people here are lucky because you prepared the data for the hackathon. But in a usual case, it would be like everyone does that for themselves. So it's not like
Yes.
one person, 60%, but 20 persons, 60%. So how could this be avoided? Is there some other way to automate it, or is it so individual that it's not possible?
Well, yeah, it's quite sad. I mean that for me also, I should also get a project and do some processing, and I look at myself and I say, oh, wow, this week from 5 days I spent 3 days just checking, cleaning, removing. People people are very creative. They don't know how to put missing value, so they put a 0, I don't know, for missing value. And then if I blindly use the data, it completely messes up the modeling. So how to automate that? Well, yeah, you could. I think many things you could make functions that. I think in this tidyverse in R, there's quite some functionality. Like while you load the data, you can add some cleaning and checking, validity checks, and like for example for dates. Date, whether the date is correct format, and you could automate absolutely. But some things are so complex that you need really human to look at it with knowledge of biology, ecology. Now we work with health data, and you really you need a human to look at it because it's just too complex to automate.
Maybe it's not so much about how users clean the data, so not about automating this process, but maybe about the data provider who could provide the data in a certain way.
Oh, this thing is all about. It's about standards. It's people using standards and harmonizing to same standard, and then having software that pushes you to. So, like if you had a software that everybody, when they load the data in software, that it has so many validity checks that the users are then pushed to tidy up the data, and then you have this international organization like GBIF, GBIF and many organizations, they force you to enter all the metadata, to enter all the fields, and that goes through validity checks, and that's the way to increase the quality. Yes.
Okay, thanks.
Anybody else has the challenges that we maybe missed? Please let us know if you think that we missed some challenge. We made this quite extensive list: overfitting, extrapolation, and usability. But if you technical challenges, do you have some challenge that we maybe missed? Yes, Marcus.
I would have one
Martin,
about the data sharing that you mentioned, and that's the data licensing and data use policies. So we're working in a context with global air quality data, for example, and here you experience that many countries have either no open license or not even a license concept at all. So that can make it very complicated to actually pull data together and use it in a coherent common framework.
Okay, but you said it's for the air quality data.
This was specific for air quality data, but
okay.
I believe that exists also in many other fields if you start collecting field data. So as long as, of course, if you're working with remote sensing data, it's easy in a sense because you only have to do with a few space agencies. But if you have to connect to many individual groups, research groups all over the world, that can be a substantial problem.
Yes, I'm aware of that, yes. We are pushing through the Open Land Map. So that's one of our flagship projects. We are pushing through Open Land Map and through Open Earth Monitor. We will be pushing to really get people to accept standards and simple setups, licenses, standards, and then also tools that can be used to import, harmonize, and bind data in an easier way. And then the data becomes more usable. And it has to go through GitHub. It has to be, almost read and write like a Wikipedia approach for everyone, so that people can fix, improve, and it's just constantly getting better and better.
Yeah, that's let's say more technological aspect. The other aspect is, I guess, more this recognition aspect, which goes into this reward scheme in science. So that people who produce data feel that they're not rewarded sufficiently if someone else then starts taking the data, using the data, publishing papers with the data and all that. So I think in that sense there's, let's say, some education necessary, but also I guess one shouldn't underestimate the time it takes to convince people to actually open up data and make it available.
Yes, I just had some people send me an email. They did a project in Africa because we built a Africa data cube, agronomy data cube. And they said, oh, we have these points. Will it be useful for you? And so then typically what I tell them first, get a DOI for your data, put it on Zenodo, get a DOI, get a publication if you can, right? And then just take some metadata standard, take some standard data format, if it's GDOC compatible or GeoPackage or something, and then put your data into that, or some simple format like just CSV, or, and then put it there, pick up some metadata standard, and get a DOI and get the recognition. Absolutely. The problem is the citations on data. Yeah, people are still, we're funded by government. Government wants that you publish in Nature and Science, I don't know. If you say, look, I made like 50 data sets used by, 10,000 people. They said, no, where's the publication? So you do have to also, but luckily now the journals, data journals, but they cost, to get the open access publication, they cost too much, if you ask me. So that's a problem. So now we have these data journals, but they still want like, I don't know, 2,000 euros for publication. Yeah. My first recommendation is Zenodo. Just register data, put in Zenodo, put a minimum. And Zenodo now supports, works as has a HTTP service. So if you put a cloud options GeoTIFF, I don't know if you know that, if you put it on Zenodo, you have a free hosting, cloud optimized data. So you have a free, basically it's paid by European citizen because it's this CERN accelerator side project, Zenodo. And so if you put it there, it will work as a cloud optimized solution. So you can put, for example, 50 gigabyte file, and people don't have to download 50 gigabyte. You can just load it into QGIS, and you can work with it. Yes, we have to stop. Yes. Thank you so much for questions. And we have a coffee break, and we continue with Ben Graller. We'll talk about KISTE project and your experiences. So coffee break, half an hour.